Presenting GlucoPulse, a diabetes risk prediction system that combines a machine learning model with a clean and interactive web interface. This project is designed as a clinical screening interface. It is not a replacement for a medical diagnosis, but it helps users understand diabetes risk based on important health measurements. When the application opens, the first thing we see is the GlucoPulse dashboard. The interface has a calm medical style, a clear brand area, and three main sections: dashboard, insights, and patient. The dashboard explains the purpose of the system. A user can adjust patient measurements, review the model confidence, and compare a patient profile against historical diabetes indicators. On the right side, the circular result panel shows the prediction percentage, the risk band, and the model accuracy. In this run, the trend random forest model reports about 88.71% accuracy. Now I am starting the patient checkup flow. This screen contains the 8 medical inputs used by the model: pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, and age. These are the same features present in the diabetes dataset. So the user interface is directly connected to the machine learning model. I am increasing the glucose value first because glucose is one of the strongest indicators in diabetes risk screening. Next, I am increasing BMI to show how multiple health measurements combine into one risk estimate. I am also adjusting age and blood pressure to create a higher risk patient profile. As the sliders change, the application updates the visible values immediately and sends the current patient data to the backend prediction API. Behind the scenes, Flask receives the patient values, checks that they are valid, converts them into a pandas data frame, and passes them to the trained random forest classifier. When I submit the form, the result dialog shows the predicted risk percentage, the risk category, and the model accuracy. For this profile, the model detects a diabetes risk pattern. The system presents this as a screening signal and reminds the user that medical decisions should be confirmed with a clinician. Now I am changing the same form to a lower risk profile by reducing glucose, BMI, and age. When I submit again, the prediction changes. This shows that the system is interactive and responds instantly to different patient conditions. Next, I am opening the insights section. This part of the project explains the data context behind the prediction. The metric cards summarize the clean training dataset. They show the number of records, the positive diabetes outcome rate, the average glucose value, and the average BMI value. After pre-processing, this project run uses 616 records with a positive outcome rate of about 51%, average glucose of 126.4, and average BMI of 32.1. The chart plots age against glucose. Teal points represent lower outcome records, coral points represent diabetes outcome records, and the dark marker represents the current patient profile. This is useful because the prediction is not shown as a black box only. The user can also see how the current patient profile compares with historical patterns in the dataset. If I change the patient glucose value and return to the chart, the dark patient marker shifts. This proves that the visualization is connected to the live patient state. Now let me explain what happens behind the scenes. The backend is written in Flask. When the app starts, it reads diabetes.csv, cleans the dataset, removes invalid zero values from important medical columns, handles outliers, and balances the outcome classes. The model used here is a random forest classifier from scikit-learn. The app trains the model once and caches it, so repeated predictions do not retrain the model every time. When the user requests a prediction, the backend returns the probability, final prediction, risk label, model accuracy, and cleaned input values as JSON. The risk labels are simple and readable. Lower risk appears below 38%, moderate risk starts from 38%, and elevated risk starts from 67%. The frontend is built with HTML, CSS, and vanilla JavaScript. It handles tab navigation, slider updates, prediction requests, the result dialog, toast messages, and the insights chart. The project also includes validation. The sliders keep values inside realistic ranges, and the backend also clamps invalid values before sending them to the model. This means that even if someone bypasses the browser and sends incorrect input, the server still protects the prediction flow and avoids crashing. The application is responsive as well. On a mobile screen, the layout stacks neatly, the controls become easier to use, and the same dashboard, insights, and patient features remain available. For deployment, the project includes package.json, server.mjs, a Docker file, and render.yaml. The Node Start script launches the Flask app locally on Windows and can run Unicorn in production. The Docker file packages the application, and the render configuration defines the cloud service and health check route. To summarize, GlucoPulse is a responsive diabetes risk screening application powered by a random forest machine learning model. It accepts patient health measurements, predicts diabetes risk in real time, explains the result with probability and risk bands, and supports the prediction with dataset insights. This project connects data preprocessing, machine learning, backend API development, front-end interaction, responsive design, and deployment readiness in one working system. Thank you.